Next, we're going to look at end behavior. So your end behavior basically is telling me, oops, and before I forget, my program doesn't have arrows on them, so I'm going to put arrows on the end of this. You're looking at what's happening on the right side of your graph, that's right end behavior, what's happening on the left. So if you picture this being on an x-y axis, as my x's are getting bigger, as my x's are going towards infinity, I want to basically know what's happening to my f of x values. Okay, so when I ask for right end behavior, this is the kind of notation you have to give me for right end behavior, and you'll give me equals whatever the value is. And in this case, since it's pointing down, my y values are getting smaller, she'd put negative infinity. We'll go through that when we get down here. Over here, my left end behavior, as my x's are getting smaller and they're going towards negative infinity, I want to know what's happening to my y values. And in this case, and it'll be equals something. In this case, I'm pointing up, so it would be towards positive infinity. So when I ask for left and right end behavior, you have to give it to me in limit notation. So let's look at our 3 examples and see how much of this you can remember to graph. And if not for right now, you can put these in the calculator and graph them. I'm just concerned about your notation for these. So let's look at the first one. This is an x cubed graph that's positive. So if you remember from Algebra 2 last year, when you graphed, if you graphed higher degree polynomials, a cubic basically looks like it has 2 humps, and since my leading coefficient is positive, it's going to point up on the right, and it's going to have 2 humps. So this is just a generic graph for my polynomial. So if I'm looking at my left end behavior, this is going to be my limit as x approaches negative infinity of my function. And since this is pointing down, my x values are getting, or my y values are getting smaller and smaller and smaller. My limit's going to be negative infinity. If I want to look at my right end behavior, my limit as my x's are getting bigger, this is getting, my y values are getting bigger and bigger and bigger. They're going up. So that's going to be positive infinity. And those are my right and left end behaviors. If we look at the next example, negative x squared plus 5, that is just a parabola upside down. And we're going to look at left end behavior. So my limit as x approaches negative infinity, I'm on the left of my function. Now this time it's pointing down, so my y values are getting smaller, just like this one was. It's going towards negative infinity. My right end behavior, as x is getting bigger, as x is getting bigger, it also is pointing down, which means my y values are getting smaller, so it's going towards negative infinity. And those are my left and right end behavior. Okay, now the last one, unless you remember how to do it, I'm not going to expect you to know how to do it. If you plug this one in the calculator, and on a test I would put this on a calculator section, this is what your graph looks like, or I'd probably give you one and just make you give me the answer. And so your graph looks somewhat similar to this. Okay, so when I go to graph this, my limit as x approaches infinity, that's, oops, and I did these backwards. On the right, it's getting bigger. It's infinity. So this one on my left, my limit as x approaches negative infinity is getting smaller, going towards negative infinity. And just FYI, this was supposed to say 16x on the bottom, not 2x. Okay. So there are my left and right hand behavior. The basic thing with these is you need to be able to either, one, do a basic graph after we finish all the way through 1-7 on these, or I either should be able to give it to you, give you a picture, or give you it on a calculator part for your test that you can plug in the calculator and get that information from there. Okay. Last thing we're going to look at intermediate value theorem. It states if f of x is continuous and your a is less than b, and there is a value n such that n is between f of a and f of b, think of a and b as your x values. So these are your, oops, let me move this over. So think of these as your x values. Okay. Then there is a number c such that a is less than c is less than b, and f of c equals n. So really what that means is if I make a table from these values, even if I don't know what the graph looks like or I don't know anything, I should be able to figure out where there is a 0. And what this will help you with is when we get to chapter 7 and you have to graph, or I mean when you get to chapter 2 and you have to graph higher degree polynomials, you'll kind of have an idea of how to know how to graph it. So I want to take f of x equals x cubed minus 4x plus 2 between the values of negative 4 and 4. I just want to look at that set of numbers. And I want to determine between what two values there's a 0. So even if I can't mathematically factor this, I could do longer synthetic division and I might never find them because they could be radicals, they could be imaginaries. So there's a whole host of reasons why you would not be able to factor this function and graph it. But making a table of values, you can kind of get an idea of where your 0 should fall. So if I plug in all of these values, I'm just going to tell you what the functions are, and I assume you know how to plug this in a calculator. You're going to get negative 46, negative 13, 2, 5, 2, negative 1, 2, 17, and 50. Okay. So what I'm looking for is your zeros, or where your f of x changes from positive to negative or negative to positive. And remember, this is your f of x. Your y and f of x are basically the same thing. So I went from a y value of negative 13 to a y value of positive 2. So that means there's a 0 in here. Let's see if there's any more. So 2 to 5 is no change. 5 to 2 is no change. 2 to negative 1, this is another change here. From here to here, there's a 0 in between this set. So there's one in between negative 3 and negative 2. And there's one in between 0 and 1. And if you look, there's also, I went from negative 1 to back to positive 2. So there's another one between between positive 1 and 2. So the intermediate value theorem just helps you figure out where your zeros are. When you get to calculus, your intermediate value theorem will also be helpful in you when you start working with first derivatives, second derivatives, and things like that. So this is the end of 1.3 video.